Today, it's our great pleasure to have Aziz Kharouf, who recently finished at the University of Haifa and soon to be starting a position at Bilkent University, who will tell us about higher order Toda brackets. The floor is yours.
Thank you, Martin. Thank you for inviting me today. Thank you very much. Okay, let's go. So higher order Toda brackets, what's the plan today? I want to start with the ordered Toda bracket to define the order with some background. Then the definition of the higher order Toda bracket in two ways. There is two common ways that people define the higher order Toda bracket. Then I will give a third definition, which use homotopy limit. Diagrammatic, I called it diagrammatic definition. And by this definition, finally, I show the equivalence between the first two definitions. Okay. This is the plan of the talk today. Okay, so let's start with the primary order of the primary Toda bracket. So given a maps F, G, and H, where the composition here is null homotopic and the composition here null homotopic, and if you choose two null homotopies, then you get the following. You have this null homotopy from the cone of X to Z. You can compose with H, so you have a map from the cone of X to W. You can also compose this null homotopy from the other side with the cone of F, because it will be the same target here, the same. Okay, so you have two maps from the cone of X to W. Both of them coincide at X. At X, it's a composition of the maps. So you get a map from the suspension of X to W. Okay, this is the Toda. This is the notation we use. This is a value of Toda, or the homotopy class of this map is the value. It's called the value of Toda. It's okay. We will discuss all the time. There's just the map itself. So it's obvious that it's not just depend of F, G, and H. It's depend of also the choices of the null homotopies. Okay. Also, I will call the maps with the null homotopies a Toda system. So if we have a Toda system like this, okay, this is a Toda system. So we get a map from the suspension of X to W, which is called the Toda. Okay. So Toda, firstly defined by the Japanese mathematician Hiroshi Toda. He want to get a new element from in the homotopy groups by Toda. Then Frank Adams serve as a differential in spectral sequence to use that. But I want to give something that maybe more shows the meaning of the Toda. The meaning of the Toda. It's to rectify linear diagram, rectification of linear diagram. So the Toda is the abstraction of Toda serve as an abstraction to rectification of linear diagram. What I mean by this, I mean if you have, if you have two maps, I will clear it. Okay. If you have two maps, F, G, where the composition is null homotopic, then you can rectify. What I mean by rectify, you can find a zigzag of weak equivalences. Okay. You can find a zigzag of weak equivalences where the composition, it's exactly zero. Okay, that I mean, what I mean by rectification. Here, the composition is exactly zero. Here it's null homotopic. But if you have three maps, if I have another map, so I can do it for this composition, I can do for this composition, but together, not always we can. Okay, we can't always. So the Toda can tell us when we can, when we can't. In this sense, now I back to the full screen. Yeah, okay. By this theorem that tell us if we have such a linear diagram where the composition here null homotopic and here null homotopic, then the diagram is rectifiable. You know what it means, rectifiable? Okay, what I explained. if and only if there is a null homotopy Toda. Okay, we can choose null homotopes that give us a Toda as a map from the suspension of X to the last target, the last codomain is null homotopic. Okay, then we can that it's a chain. We can think as it's a chain in the homotopy category. We can what is get it up, what lift. We can lift it. Okay. This is we can. Here I have an example in the world of chain complexes. We have here 3 maps. It's obvious that the composition here not 0, but it's null homotopic. One can see that the composition here is null homotopic. The composition here is null homotopic. But if we want to check if it's rectifiable or not, we can replace it up to homotopy by something that the composition is exactly 0. We have to calculate the Toda, all the Todas, because I come back to the there is something in chat. Someone.
Oh, it was just a clarification about the word linear in that sentence, but you just mean the shape of the diagram, just a bunch of arrows.
Linear, I mean this. Okay.
Yep.
The shape
Got
of
it.
Thank you for responding. Yeah. So we see if and only if there is one choices of this. Okay. So we have to calculate all the, but it's not difficult in the world of chain complex to do that. And I did it. One can do it, and it's just we get just the only class map from the suspension of this to this. It's just the identity. Okay, so it's tell us that we can't rectify this diagram. Okay, yeah, one can do the calculation. Okay. So now I want to give another description for the ordinary Toda using homotopy cofiber. If you have 2 maps with a null homotopy, so then you have this square. Okay, it's 2 maps. The composition it's through the cone of X, come through the cone of X, so it's null homotopy. One can apply the homotopy cofiber. We get the map from the homotopy cofiber of this to the homotopy cofiber of this. So we get this map. I want to denote this map by the alpha because it depends on F, G, and F. Okay, and one can do the same in the other direction and get the map from the homotopy cofiber of F to Z. Here we can choose it to be Z because we can choose it to be cofibration. So, and this is contractible. So the homotopy cofiber is Z. Okay, so I called it beta. Then if one have this Toda system, what we call Toda system of the Toda, we have 3 maps with 2 null homotopies for the composition. Then if one calculate alpha of the first for F, G, and this F, and then the beta of this composition with this null homotopy, okay? Then what we get the map from the homotopy cofiber of G to W. And if one compose this, get the Toda. One can prove that. It's easy to prove. Okay, the same Toda that we defined before. So this is another way to describe the Toda. We split this, but it's good because it will serve us to give a recursive definition later. Okay, so the proposition tells us that the composition here between alpha and beta is the same Toda we defined before. Okay, now I'm going to the higher order Toda bracket. People extend the definition of Toda bracket in 2 ways.
Sorry, Aziz.
Yes,
can you go back to the previous slide? I just got confused about that middle object and the composite at the bottom. Can you go over that again? So that middle object
is this here?
Right, that's the cofiber of G.
The homotopy cofiber of G, yes.
Right, but then
because here it's not, because I show the definition here, the beta of F, G, and F for the fair. But if you do the beta for this, for GH,
Oh, yeah, it's
so
the beta
from
for
the
that other
yeah.
composite. Yeah, okay, sorry, that notation
Yes,
tripped me up. Thank
so
you.
from, sorry, yeah, it's confused. Yeah. So,
That's why I got it.
thank you. Yeah. Okay, so we get this. So here's the composition. Maybe it's the same alpha you define in your article, but you maybe defined it's from X to, and then you get you with the suspension of alpha. It's the alpha of mine. It's the suspension of alpha in your article. Yeah. So, okay. So we continue. The higher order Toda bracket, people define the first way is cubical definition. It's a definition that one can do in any category enriched by simplification or cubical. What I did here by cubical sets. Okay, so in infinity category, one can do that definition. We will see. Sorry, I didn't say it before. I didn't say before. One can think that I work in topological spaces. Okay, everything is topology, or in pointed model category. Maybe with some technique property, it's to be left proper. Don't think about it if you're not familiar to this, but one can think everything I do in topological spaces or chain complexes. I gave already an example in chain complex. Okay. So this is the first definition we will give higher order. Then we define a recursive definition using this alpha beta I already defined. And here we generalize the rectification, because one can ask himself, what about maybe that one of the reasons that people want to extend the definition of the Toda bracket, because the Toda bracket, we saw the ordinary Toda bracket serve as a rectification for linear diagram with 3 maps. What about more? So it will be the Toda, and one can see by the recursive definition, not by this definition. It's easy to see, but we will see later that the two definitions coincide. This, okay. Okay, in this talk, we'll do that for 4 maps. And if someone gets the idea for 4 maps, can generalize is for, any number. It's okay. Okay, so let's start with the definition, the cubical definition. I want to use yprod to do that. Okay, I can clear that. I want to explain what's going on here. So we have now 4 maps. F, G, H, K. Okay. So let's see, K, where we have null homotopy here, F for this, F here, null homotopy G, here, null homotopy H. Okay, null homotopy for this. So then for the first, one can search the Toda. So we have here the composition of Fj. This one can think this is X for me. Okay, sorry, the point is X, and we have a map to the W. To Z, sorry, the map from this to Z. Okay, so we have on the cone we put here F. Okay, and we have this, the composition GH, and in all homotopy to the point to G. Okay, and when we compose this with H here, and compose this with F from here. So I have to put here CF because okay. And then we glue together, we glue together and we get, so I can put this here because the same at X is the same. Now, to define and we get the Toda, the ordinary Toda for the first 3 maps. So to define the higher order Toda, we need here null homotopy for this. So we need the map from the double suspension of X, okay, to W. Here we have a map from the suspension of, maybe I have to write it here. This, in this side, we have this map, okay? From the double suspension, you have to fill this, okay? This is a cont by new null homotopy. I called it to, it's a map from, it's a map from the double suspension to W, okay? So we have this. In the other side, we can do the same in the other side, and we do, I can do it. We can do the same for G, H, and K, okay? The same. So we have here G, H, K. We have here G composed with K, and we have G this with H, so the cont of G with H, okay?
Sorry, Aziz, just to make sure that I'm following, are you saying that this red F superscript 2 is sending everything to the base point at the top edge and the right edge of the square?
Again, what? Again?
So that F2 there, are you saying that its value restricted to the top edge of the square is all the base point?
Yeah, it's all here, the post.
And the right edge as well, right?
Yeah, all this is a point, base point, yeah.
Got it.
This point.
Okay.
Yeah, and here you have a Toda, the primary Toda. Yeah.
Okay, that's what I thought.
Okay?
Thank you.
The primary Toda. Here we do the same, so we need another higher order Toda. So we need another one, G2, I called it. So it's a map, G2, it's a map from the double cone of Y to V, okay? Here, okay, sorry, here we have this. And we can compose, we now compose here this with K, with the last map, and this with the first map with F, okay? So we compose this with K, here, K, this with K, this with K, this with K. So we have here a map from, this, a map from the double cone of X to V. And here we can compose with F, the first. So here it's F, but here I have to put a cone of F. Of course, here a cone of F, and here a double cone of F. And we have a common here, a common where we have a common, you see? Yeah, this is the common side, common cone, yeah? This side and this, you see? We have a common cone. Yeah, so we glue together, but we have another side to be, because this is not, we want to the double suspension, something like a double suspension, okay? So I glue together, I can show you the picture in the PDF. I direct PDF, so here is the picture, yeah? But this is the two sides. I have this side and this side, but I have another side, which is the composition of two one order null homotopies. Here I compose two order null homotopy with a map. Here there is a two order null homotopy, but here two one order null homotopies I compose to fill this, and I get from this, which is it's equivalent to the, I called it L2X, but it's equivalent to the double suspension. This, okay. If this is X, if one can think as this is the point of X, this is the cone, this, okay. So this is the equivalent to the double suspension. I don't familiar with this, who asked, is this an operator in the, you mean this with the, I don't, you mean, now I mean there is a point in the other side. Yeah, you can think at, maybe I answer you, you can think at it's a map from the cube, the X tensor the cube, and we put in the all the other side the point in all the other side, and here also point in this side also. Okay, I answered you, or no?
Sorry, okay, what I meant is when I meant in the background, I didn't mean in the background of your picture. I meant, can this be phrased in terms of an operand? That was, yeah.
Yeah, I'm not familiar with opera. Sorry. So I can't answer you, but there is a point. What is opera? You mean it's a mathematics, yeah? Or you mean or something I maybe didn't get?
It's mathematics, yeah.
Yeah, no, yeah, I know, but I'm not familiar too much with this. Okay, sorry. So we get this map. This is from the double. This is something equivalent to the double suspension, to the double suspension. Yes, to V. We get this map. Okay, this is a second order Toda bracket. Okay, for four maps. So to define this, we have 4 maps and 3 one-order null homotopies and 2 second-order null homotopies. Okay, this is called the Toda system. Okay, these the maps and all the null homotopies we need. We called it Toda system, cubical Toda system. Okay, because it's a cubical definition. Yes, there is someone. Okay, thank you. So now this is I will denote this by t of x. I mean this the underlying here diagram. Okay, and f is all the null homotopies. Okay, so I will use this notation from now instead this because it's long. Later we will define equivalence relation between such Toda systems. Okay, if we have 2 Toda systems, such a diagram with null homotopies and the other one, so how we can see that it's equivalent or not. And of course we want to define equivalence relation that induce equivalent Todas. Okay, we want later we will do that. It's by the third definition, by the diagrammatic definition. Okay, let us now do the recursive definition for Toda bracket. The recursive maybe it's easier to understand because it depends on alpha beta. So if I have 4 maps and I have null homotopies for all composition, then I need the alpha of the first one. So you remember the alpha, what I mean, it's from the cofiber of this to the here I will take the cofiber. It's because I make everything. It's every square is cofiber square. Okay, so I can take the cofiber. It's heavy meaning of the homotopy cofiber. So I need the alpha of this square of the first. I need alpha and beta of the second square, and the beta of the third one. And then if I compose this one with this, I get the Toda. This with this, I get the Toda of the first 3 maps, the ordinary Toda. And if I compose this with this, I get the Toda of these 3 maps. Then I need to define this as before, as a cubical definition. I need the Toda to be null homotopic, the first order Toda to be null homotopic, this and this. So I choose null homotopy for this. But you see, it's not the same kind of null homotopy. Okay, and then I need alpha of this cube and beta of this cube. So the alpha of this cube is from the cofiber of this, which is the double suspension, to the cofiber of this beta, and here I want this from the cofiber of this to the cofiber of this. Okay. So this is beta 2. I call this beta 2 and 2 here because it's a second order beta, like I said. Okay, here one can see that this is the same because it's both come from the same square. Yeah, from the square. If you would here, the cofiber of this equal to the cofiber of this. Okay, so the composition here it's the Toda. Okay, so this is by recursive way, and one can imagine how we can continue. It's a recursive way to define a Toda. Yeah, maybe one something I want to say. Yeah, so I want to say that this, you see, we have equivalent with the cubical definition, equivalent domain and equivalent codomain, because if we back where it's come G2 from this, so equivalent to the cofiber of this, because this is contractible. This is cofibration. So the cofiber of this is equivalent to V. Okay. So as before, but I want to show later that the maps is equivalent, not just domain, the codomain, this map and the map here where we defined before. Okay, let's continue. So there is a question or something. Ah, thanks. Okay. So also we have here recursive Toda system. It's we need, as we see, 3 maps. The same first order non-homotopy is the same, but second order it's not the same. We see a cubical. We need double from the double cones here from the cone of the suspension. And we will call it recursive Toda system, okay? And all the time I will use this with tilde. It's called tilde, yeah, like the latex, yeah, tilde, or in English, yeah, tilde. I use tilde for the recursive Toda bracket, okay?
Aziz?
Yeah, yes.
So if I look at your Toda systems in both definitions, they build in all the choices involved, right? So ultimately, if I give you a, say, cubical Toda system, that represents a single element in the long bracket, right?
Yeah.
So, okay, so all the choices are built in, right?
Yeah, I don't go with all the choices. That's with one, yeah. Yeah, but
right, okay, but yeah, so those choices together define a single element of the long Toda bracket.
You mean here or in the cubical?
Well, in both cases,
yeah.
But let's say the cubical Toda system.
Yes.
A system has all the choices built into it, right? So ultimately, all
the choices of null homotopies, you mean?
Yeah, and higher order.
No, one choices. That's the Toda system. Toda system, I mean one choices of, not all.
Yeah, sorry, I meant all the choices have been made along the way, so that ultimately a Toda system produces a single element of the long Toda bracket. That's my question.
Yeah. Single element. Yeah.
Okay, yeah. That's what I thought. So
you mean by the long, maybe the long, all the choices, yeah, all the Todas.
Yeah, exactly. The long Toda bracket to me is all possible homotopy classes you can build that way.
Yes.
Okay, that's what I thought. And I had a second question also. As you mentioned, I worked on the stable case in a stable model category. And if I remember correctly, it's been a while since I worked on that project, but for the recursive definition, I think it was enough to remember just that one factorization into 2 steps.
Yeah.
So that you didn't need to build in all the previous. I mean,
you did it in many ways, yeah.
Right.
Remember, you did.
I think for our family, the Toda family, we had just the data of that factorization in 2 steps. Whereas here, if I'm looking at this correctly, if I'm reading this correctly, the recursive definition builds in all choices along the way. You have your capital F, your capital G, your capital H, and then the F tilde 2 and the G tilde 2.
Yeah.
Whereas, at least based on the stable case that I worked on a couple of years ago, I might have expected that you only build in the factorization in 2 steps that was displayed either on that slide or the previous one. The factorization in 2 steps.
Here.
No, in the recursive definition.
The recursive definition. So here I get this alpha, which is a dependence. This is a choice of F, and this beta is a choice of G, and then this is Toda, one value of Toda. This is okay.
Right, but can you go to the 2-step factorization? I think it's a little bit further down the road. That factorization exactly. I might have expected, at least based on the stable analog, that in your recursive definition, you just need to remember that bottom displayed equation, the factorization as alpha 1, 2 and beta 2, 2.
Yeah.
But if I read the next slide correctly, that's not what you're doing. You are building in all the choices along the way, the capital F, capital G, capital H, and the F tilde 2, G tilde 2. Am I understanding correctly that you really need all of those choices, or could you just get away with defining some kind of Toda family as those composition in 2 steps as in that bottom equation? That's my question.
No, I'm just one choices. Yeah, just one. You mean the choices of the null homotopies, yeah?
Yeah, exactly. Exactly.
Yeah,
So
no, one choices. Then if you want to get all the Toda, if you want to get this, you want to get this FG. Sorry.
no, so that was my previous question. My current question is a different question. My current question is about your definition of recursive Toda system.
Yes.
In your proposed definition, you make capital F, capital G, capital H, F tilde 2, G tilde 2 part of the data. I might have expected, based on the stable analog, to not do that. And just remember those families of compositions in 2 steps, as in this equation at the bottom of that slide, right there. And that's exciting to me, because maybe in the unstable case, it's not enough to remember those 2-step compositions. That would display a crucial qualitative difference between the stable and the unstable context. And I'm wondering if that's the reason, or if it's more for convenience.
And yeah, if you want to get here.
Yeah,
No, I have to make it sure. I don't see how I can do it as you did. Yeah, I don't.
Okay, so
you know, I remember that I defined this, and then I thought that it's in you, the definition, and then I saw it in your article. Yeah, when I defined. So, but then I thought how to compare. I think this is the way. Yeah. Even here, I work
to give credit where it's due. Our construction is basically going all the way back to Joel Cohen's paper, so it's not.
Yeah.
Right.
Yeah,
it was
also,
a well-known
I didn't
construction.
know before, but yeah, also, yeah, someone told me that I read. Yeah, it's maybe even a special case of this. It's something more. Cohen? You mean?
Yeah, Joel Cohen's paper introduced those long brackets.
Something generalization of this. Yeah.
Right. Okay. But so you're saying that a priori you don't see a way to not encode capital F, capital G, capital H, and all that data as part of your recursive system.
Yeah.
Okay. Yeah, that's fine. We can talk about it later. But okay. There's no obvious way to get rid of that information.
Yeah.
Got it. Thank you.
Okay. Thank you. No problem. So we have this recursive Toda system. It's I mean all the null homotopies we need. Okay, so we will use this notation, and as well later we will define equivalence relation between Toda systems. Okay, which induce the equivalent Todas. Okay, yeah, and here is the theorem. We have the theorem for this definition, not for the cubical definition, that if we can choose a null homotopies where the Toda here it's a null homotopic, the Toda, then we can rectifying this diagram. Okay, we can.
What does rectifiable mean?
What?
What does rectifiable mean?
Yeah, what I explained before, that you can change it up to homotopy by zigzag of weak equivalences to something that the composition is exactly 0, not just. Okay.
Exactly what?
0, exactly constant, not just null homotopic. This here, in the situation of the composition, it's null homotopic here and here and here.
Right.
Can you, not always we can, for every such a diagram, we can replace up to homotopy, which something where the composition is constant.
Okay? Understood. Yep.
Yeah.
Okay.
Okay. So now the diagrammatic description, that's something new, the diagrammatic. So now back to the ordinary Toda. We have 3 maps because I want to show it in the primary, then I'm going to the 4 maps. The Toda system is this, yeah? We have this for the Toda system. Right. But I want to look at this as this. I want to look at this as 2 maps of maps. Okay, here we have a map from this, yeah, here from this map to this map here. Okay, this square, I can think about it as a map from this map to this map, and right. This I can think about it as a map from this map to this map. Okay, so right. I want to organize it like this. So I want to do something similar for 4 maps, okay, for the 2 second order Toda system, okay, something similar. So in the case of four maps, we have three null homotopies, first order, and two second order null homotopies. So for the first Toda system, for these three maps, we can organize this in this way, as we saw. And for this, with the corresponding null homotopies, we can organize it like this. And now where we can put this look as a null homotopy for this composition. We can think about this as composition. So look where F2, yeah? If you remember, F2 have one side of F2 is one side in the cone is this. Here it's an inclusion, sorry, this F it's belong to this map. Here is the inclusion. So one side is this, if you remember the cubical definition, one side is this, the null homotopy with H, and other side is this, okay? So this tell us all the relation between the null homotopies here by this commutative diagram. And also G is here. And we see here that one can think about it as a map from this square, you see, this square, analogous to this map, yeah? So this square to this square. And this square we have here also, you see, this square is the same as this square, yeah? It's include all the middle null homotopies, all the middle and maps, GH and the middle null homotopy, the square. It's here also, and we can think about it as a map from this square to this square, okay? So I want to organize this by this way, okay? So the Toda system, the cubical Toda system, all the information, all the data of the cubical Toda system, we can organize by this way, okay? So you can compare with the ordinary, okay, Toda, you see? Instead this, we have this, okay? And here in the middle, we have G, here we have all the middle maps and null homotopies, okay? And here we have something like this. So here, you see all the, here, everything is contractible as here. Yeah, one can think and how it's building, because here how we have all the first maps and null homotopies also here, okay? Okay, so why it's good to do that? Because now we can define equivalence between Toda system, okay? How we can define equivalence if we have two Toda system, okay? Like, okay, here what I said is that this encode in this diagram, this encodes the cubical Toda system, yeah. Okay, so if we want to have another Toda system, and these two Toda system are equivalent if and only if the diagrams, the corresponding diagrams are equivalent as the diagrams. Okay, there is a zigzag of equivalence between them, okay? So this is the definition, okay? And we expect that this will give us the equivalent Toda, okay? Induces equivalent Toda. So we will see, but then the question, how to define Toda by this, by using this. So let's go back again to the first, to the primary Toda, to the ordinary Toda. How we get from this, the ordinary Toda, I show you, if you remember the proposition at the first, that we can take the alpha and the beta and composition. What is the alpha? We take the cofiber of this, the homotopy cofiber of this. The homotopy cofiber of this, we have a map. This square inducing map from the, and this square inducing map from the homotopy cofiber of G to the homotopy cofiber of this, which is W, okay? And the composition is the Toda, so we can do the same here, okay? We can do the same, but in order to do that, we have to define, let me back here. So we can do the homotopy cofiber of this to the homotopy cofiber of this. There is a map, and there is a map from the homotopy cofiber of this to the homotopy cofiber, then we compose and get the Toda, yeah? But what is the homotopy cofiber of square? First, the cofiber of square is the column of this, as maybe many of you expect, yeah? Okay. the colimit of this, and the homotopy cofiber of square is the colimit of this. Okay, it's the homotopy version of the cofiber.
Sorry, Aziz.
Any question? Yeah.
I don't see immediately if that's the same as what's also called the total cofiber of a square, where you take cofibers in both directions.
Or...
Yeah, total cofiber of a square. Is that the same? Let's see. The total cofiber of a square.
I don't know what is the total, but I can
let me tell you the definition. Oh, yeah, it's fine.
Okay. If you have, I can say that if you have this in chain. Okay, sorry. If you have this in chain complexes, for example, you have this square, and you get, because it's commutative, so you can get this, yeah, plus Z to W, this double complex. So the total of this is exactly the cofiber, the homotopy cofiber. So the total of this.
Okay, that's an interesting example. The construction I have in mind, so let me just give you the definition. Total cofiber of a square is obtained by taking, say, horizontal cofibers and then the vertical cofiber, or vice versa.
Yeah. It's the same. Yeah.
Oh, it is the same. Okay.
Yeah, it's the same. Yeah,
Got
it's the same. If you take the cofiber of this map, for example, F or here H, yeah, and then you take the cofiber of this, yeah, it's the same. Yeah.
Beautiful, thank you.
And you can think about it, if you, the meaning of this is like this, you have the cofiber of one map is it's something that the composition here, the universal one, where the composition here it's 0, yeah? Okay, the universal one, it's okay. But, and here it's for Toda, it's the universal one where all the composition here have to be 0 with this, okay? Yeah, so that's the meaning of this. Sorry, yeah, I back. Okay, so this is, we need to know the colimit and the homotopy colimit. This is the version. For example, the cofiber of this is a double suspension. So one can calculate in your way, Martin, yeah? So this is from here, the suspension to the cone of the suspension, and then you take the cofiber in this side and you get the double suspension. And the homotopy cofiber, it's what I defined. You remember this L2X, yeah? Okay, so this is the homotopy cofiber of this. If someone take the square to be cofibrant square, so the cofibrant of the square is the homotopy cofibrant, okay? If the square itself is cofibrant as a square. So, okay, so to get the Toda, we apply here the homotopy cofiber. We have from this square to this square a map, it's induce a map from the homotopy cofiber of this square to the homotopy cofiber of this square, and induce a map from the homotopy cofiber of this square to the homotopy cofiber of this square. And if some, here I mean the middle square. If someone compose, get the cubical Toda, okay? So in every order one can do that. And the proposition that if we have equivalence Toda system, then we get the equivalent Toda. Okay, it's obvious because we use the homotopy cofiber. We use the homotopy colimit. Yeah, so it's obvious. I think. How much time I have?
About 6 minutes or a little bit more around. Yeah.
6 minutes. Just okay. Yeah. Okay. So this is the third definition. Now I want to show you how to make equivalent. But before, I want to do the diagrammatic description also for the recursive. Maybe now it's not easy to compare, so I can show you. I don't expect someone to follow this, what's going on, but here there is all the null homotopies of the. Here we have this. Here we have this as the cofiber here. Yeah, as Cohen we glue it. We put it here. So we have also diagrammatic. We can do a diagrammatic. We encode the data of the what's called the Toda system, the recursive Toda system in diagrammatic way. We can do that, and also to do equivalence relation that induce the same Todas. Okay, we can do that. And by applying the cofiber here, I can apply the cofiber, and it's have a homotopy, meaning it's okay. One can see that okay, it's like the homotopy cofiber here in this case. Okay, and get the recursive Toda. And now how to go from one to other? Now use the diagrammatic. That is the meaning. So if we have a cubical Toda system, we can get a recursive Toda system by the diagrams. I have this corresponding diagram for the Toda system, and I can here like collapse something, replace this by take the cofiber of this, okay? And here also take the cofiber of this, and here maybe the cofiber of all this square, okay? And get a recursive Toda system. And one can see that also we get the Toda, equivalent Toda for them, because if someone, we have a map from the homotopy cofiber of this to the cofiber of this, yeah, okay? And here from the homotopy cofiber to the cofiber of this, okay? So we have is like a square between the Todas where the maps is equivalent, okay? And it's factorial way, you see, yeah, it's factorial because we use here the cofiber, and it's in factorial way. So I call the factor, it's R from the Toda, cubical Toda system to recursive Toda system, and give me this equivalent Todas, okay? Okay, now how we can get from recursive Toda system, how we can get a cubical Toda system. So it's by cofibrant replacement, what it's called cofibrant, yeah? Cofibrant replacement. I can, here we have a recursive Toda system. So we have this, the corresponding diagram. And we can do this. We can choose here this to be cofibrant replacement, okay, for this square. And we can choose this, yeah, so it's in factorial way. I choose this, and can continue in factorial way, but then I have to do choices here. Here I have to do choices to choose here to continue the cofiber replacement. Yeah, and there is a choices here. It's not factorial way, okay? Okay, so then we have the following theorem also. It's the inverse way. If one give me recursive Toda system, then there is the cubical, not in factorial, there is the cubical Toda system, what I built here, okay, this, and we have this, okay, and we have this, and one can show that is reverse. If we have a recursive Toda system, okay, this, oh, sorry, this recursive Toda system, this we still, and one choose this corresponding cubical Toda system and apply R, the factor from the cubical Toda system to the recursive, so you get something equivalent. Yeah, even if someone do the other direction, first you have a cubical Toda system and apply the recursive and get something, you can choose this to be the corresponding one. So you get something equal. You can choose this to be equal. Okay, so that's it. So we show this shows the equivalent between them.
No, what do you mean by can be? That leaves it kind of ambiguous.
Can what?
You say that a corresponding cubical Toda system can be.
Yeah, can
Maybe.
be, because if I know what you mean. If you have this, okay.
Yeah.
You have cubical Toda system,
right?
Cubical Toda system, and you now apply R and choose, and you get a recursive Toda system, yeah. And you now want to go back to get cubical Toda system as a cofibrant replacement. So you can choose this to be the cofibrant replacement of this.
Okay, so it's a choice.
Yeah, it's a choice. Yeah, it's a choice.
Okay, that's
so
all.
In one direction, it's a choice. In one direction, it's something natural. Yep.
Yeah. Fine.
Yeah. Okay, yeah, that is, yeah, okay. I finished. Thank you very much for listening.
All right, let's unmute ourselves and thank Aziz.
Thank you. Since the time, my first time. Since the time.
Thanks, Aziz.
Quite on time. So we do have time for questions. Are there any questions for Aziz? I think I've used up my allotment, so open the floor.
Yes.
I have two questions. The first one is your initial. The first one is like a really easy question. So, at the beginning, you gave an example of something that isn't rectifiable.
Yeah.
And so I guess you can you do that? You did that over Z. Can you do that over a field as well? Or over a field, would everything be rectifiable?
Yeah, I think, yeah, because, over a field, no, I need it to be Z here, it's obvious, I need, but over a field, yeah. No, over chain complexes, over a field, you can, no, I think you can find the Toda that it's not rectify. There is a Toda there, okay? There is a differential and there is a Toda. No, it's I don't have now example, but I thought about something like this, and no, there is example of Todas and that not the coset here, not this maybe not corresponding this.
Yeah, it couldn't be of that simple shape, just because if it has that shape, the obstruction would live in an X1 group. But yeah, what about more complicated chain complexes?
Here, yeah, but in chain complexes, it's easy to calculate the Toda, all the Todas, because you have, it's a coset, all the Toda, it's together, because if you choose here in all homotopy for this, you can choose all the other null homotopies by map suspension from the suspension of this to this, and you can add this. Okay, if you choose one Toda, you can calculate all the Toda. It's just a coset. Okay, so in vector spaces, no, I think there is examples as Toda not vanishing. It's not a coset. Okay, so it's not. You can find example like this. I think, I'm not sure. I can think about it. Okay.
Okay.
Later. Yeah. But no, in this example, yeah, I want this to be Z, not a field. Yeah. If you
sorry, I think sorry, I need to correct something I said. The Toda bracket will live from the suspension of the domain into the target. So in this case, it's actually in a Hom set. I take that back. Right, because of the suspension, you end up in X0 or Hom in the derived category. So yeah, I was off by one. Okay.
Yeah, let me just, if this is a field, you mean, so what we get here? We get also, no, why not the same? You get here, it's 8, okay, from the field to itself. Yeah, why not? It's not, I know, I think it's the same example. Well, because you just choose, why I choose Z? No. It can be a field, yeah, because, and then you get just this, no, because you can choose here 1, here 0, sorry, and here 1 to be null homotopy. Okay.
So you just tensor with Q and you'd get something that's not rectifiable.
Yeah. What's the problem? And you get at the first the identity from this to this. I calculated it. Yeah, the identity from this to this, and in the it's not here. It's no. It's still, what is the homology here? If this is that is a problem, maybe it's no, because you get this 0 and this 0 if this is a field. Yeah. No, it's not work if this is a field, because this is contractible, so the identity will be null homotopic. No, if this is a field, so this, but I think we can choose another example that it's not rectifying in the field. but it's not a good example. Yeah, the other, you have another question?
Well, this is a little bit weirder question that I'm not, it's more vague. I don't know, like, can you, I'm just trying to think about this. Is this some kind of thing that, you know, you is related to infinity categories or something? I mean, like these are like higher order things, and, you know, your equivalence classes of your diagrams, is there like a model category structure where the weak equivalences would be your equivalences of Toda systems? That's kind of two questions.
Equivalences of Toda systems.
So would you, you know, do you have a model category and the equivalences would be like equivalences of Toda systems, something like that? I'm just trying to think about like how much, you know, like, because you kind of have, you know, in the Toda system, there's a lot of choices, but if you take a model category and then the homotopy category of that, then you can still keep the information of all the Toda brackets, but just make it so that it's kind of unique up to isomorphism. That's the idea. Do you have something like that?
I did thought about something like that before. I didn't think, but yeah, I think, okay, you can do in this, maybe you mean, yeah, the cubic before, or by going to the diagrammatic, or in this definition?
Well, like I said, it's a little bit of a vague question. I mean, the idea is like, you know, when you get a Toda system, there's a lot of choices. So eventually you get a Toda bracket. But then what happens if you want to, you know, if two things are equivalent as Toda systems, then they give the result of the Toda bracket will be the same.
Yes.
So it's kind of like something where you want to say, you want to have a category where you have the Toda systems as a model category, and then, you know, maps between them would be like the weak equivalences, so that you can get, so that when you take its homotopy category, you'd have like, you know, the unique objects.
Unique Toda system, unique.
So that it kind of like gets rid of the lack of uniqueness when you take the model category, but it still takes into account the fact that you have to make all these choices. So then I was kind of thinking that's kind of like what infinity categories do, but I don't know. So that's as I said, it's a very vague comment.
Mm-hmm. Yeah. Just a minute. Yeah. If you take this, I don't think so, because there is you have to build the Toda itself. It's something that you have to build in the category itself, not to going. You can do it. It's something that it's invariant. Okay, all the Toda. If you take all the Toda, maybe I didn't do here, but if you take all the choices here, okay, all the choices. So this is the homotopy class of this, and all the choices, and as this set. So it's invariant. Okay, it just depends on the homotopy class of this linear diagram. Okay, this here there is a k. Okay, sorry. So of this diagram, but as a Toda, you have to build it in the category itself as a Toda.
Yeah. So what I mean is, for example, you could take a category whose objects are Toda systems.
Yeah.
And then the maps are maps between Toda systems.
Maps between Toda systems, the maps. Okay.
So you have
and then in this category, but okay.
I mean, there's a little bit of that happening, right?
No,
in your diagrammatic,
there is need to be what?
In your diagrammatic description, you're looking at honest diagrams in that model category, and your weak equivalence relation is just a usual notion of weak equivalence between diagrams.
Yeah.
So there's a little bit of that happening, but I think Don's question was going further than that observation.
Yeah. But then what you get from this if you do that? I don't think that it's good to do that from my view. Sorry, but maybe I don't get your point. Good. What you get from that?
Oh, well, what do you get from? I don't know. I mean, it's like that's kind of like, you know, because you have so many choices, and then once you mod out by weak equivalence classes, then you know, the isomorphism classes are more, don't have choices. So that's kind of like, you're going to the homotopy category at a different place. So then you could ask,
maybe this is good to just one choice for all, one representative for all choices.
I mean, that would be picking a representative is like picking a homotopy class, a particular space that's in a homotopy type. Right, but this is just in a diagram category. So
maybe can you ask the question? Then you see more if two not equivalent Toda systems can give you the same Toda, the equivalent Toda.
Yeah, for example, right? That would allow you to ask that kind of question. It just kind of puts what you're doing.
You can do. I don't know. Maybe if you go to the techniques, there is a problem. I don't know because I didn't try to do that before. But I think you can do. Why not?
All right, that is all the time we have. So let's unmute ourselves and thank Aziz again for a very nice talk.
Thank you very much. Thank you. Sorry for my English.
I understood everything. And thank you all for coming. All right.
Thank you.
Take care, everyone.
Thank you for inviting me. Yeah, it's a pleasure.